The transformer is one of the most important electrical components. Since its invention in 1885, it has allowed us to transmit power across continents and distribute electricity to millions of homes. Faraday's law of induction, discovered in 1831, describes the induced voltage effect in any coil due to a changing magnetic flux encircled by the coil. It is a simple circuit by today's standards, but to build one, expert craftsmanship is still required, especially in developing countries. The process begins with long, thin strips of electrical steel. A worker uses a heavy-duty shear to cut these strips into precise, shorter lengths. These will become the vital magnetic laminations for the transformer's core. Next, a smaller shearing machine is used to cut some of these plates into smaller rectangular shapes. These are known as eye laminations. The larger rectangular plates are fed into a punch press. With a satisfying thud, the press stamps out two rectangular sections from one side, creating the classic E shape of a transformer lamination. Workers then begin the tedious task of stacking the E laminations. They are placed back to back, slowly building up the required thickness for the transformer's central core. To ensure the core is solid and perfectly aligned, the stack is placed into a custom vise. A worker taps the edges flush with a specialized core alignment tool, and then tightly binds the stack with strong strapping tape. Now, the eye laminations are inserted into the open ends of the E stacks, completing the magnetic circuit. These assembled core sections are then stacked vertically and secured tightly with heavy metal brackets and threaded rods, forming the robust framework of the transformer. Meanwhile, the heart of the transformer is being created on a coil winding machine. A worker prepares a plastic bobbin, lining it with professional-grade isolating paper. Thick enamel-coated copper wire is then fed onto the machine, which rapidly and meticulously winds it around the bobbin. This creates the primary and secondary coils. The machine keeps a precise count of the turns to ensure the correct electrical properties. Once the winding is complete, the coil assembly is ready to be integrated into its magnetic core. A worker prepares to insert the coil into a new arrangement of steel laminations. He places the coil onto an E-shaped stack, then begins the intricate process of interlocking more E and I laminations around and through the center of the coil. He works carefully, weaving the plates to minimize any air gaps in the magnetic field. A professional plate weaving tool is constantly used to ensure a tight, dense core. Once fully assembled, wooden edges are driven into the gaps between the coil and the core. This critical step prevents the transformer from vibrating or humming during operation. The final step for the transformer assembly is attaching the mounting brackets. Strong metal frames are secured to the top and bottom of the core using long bolts, providing a sturdy way to mount this heavy component. In the electronics department, workers assemble the printed circuit boards, or PCBs, which act as the brain of the Stabliser. They meticulously insert electronic components like diodes, resistors, capacitors, and microchips into the board. Once populated, a worker uses a soldering iron to permanently connect each component's leads to the copper traces on the back of the board. Back at the transformer, it's time for wiring. A worker strips the enamel insulation from the ends of the thick copper coil wires. He then solders these ends to the heavy-duty, flexible wires fitted with metal ring terminals. These will connect the transformer to the voltage-regulating relays. The protective casing starts as flat sheets of galvanized metal, A worker uses a punch press and a press brake to stamp out ventilation slots and bend the sheets into the top, bottom, and side panels. These raw metal pieces are hung on a conveyor and passed through a powder coating booth, receiving a durable, baked-on finish. Final assembly gets underway. A worker takes the base plate and mounts a series of heavy-duty electromagnetic relays. These are the switches that will select the appropriate transformer tap to regulate the voltage. Next, he carefully lifts the heavy transformer and bolts it securely to the base plate, next to the relays, beginning the complex wiring process between them. Another worker prepares the front control panel. He expertly applies a decorative and informative graphic overlay. Using a knife, he precisely cuts out the openings for the analog voltmeters. He then installs the meters, securing them tightly from behind. The front panel is brought to the main assembly, and the intricate task of connecting all the systems begins. The worker wires the front panel to the PCB to the relays, and the relays to the main power connections. He uses a soldering iron for the final, precise connections on the circuit board, which is then mounted securely inside the casing. Before the lid is closed, the stabilizer undergoes rigorous testing. It's connected to a variable power supply. A technician manually fluctuates the input voltage while observing the stabilizer's output. He listens for the relays clicking into action, confirming that the unit automatically adjusts to keep the output voltage stable and within a safe range. With the test passed, the top cover is screwed into place. The finished automatic voltage stabilizer is placed inside the protective plastic bag, packed into a sturdy cardboard box with foam inserts for safe transport, sealed, and is finally ready for the market.